Good morning, everyone. My name is Vadim Karpushenko. I'm a developer evangelist here at Intel Corporation. I welcome you to our webinar, Deep Learning 101. Today, our presenter will be Andres Rodriguez, and he is a deep learning solution architect with Intel Data Center Group, where he designed deep learning solutions for Intel customers and provides technical leadership across various Intel teams that are working on deep learning. Andres received his PhD from Carnegie Mellon University for his research in machine learning, and prior to joining Intel, he was a deep learning research scientist with the Air Force Research Laboratory. I remind you that there is a chat window available, so if you have any question during the presentation, during this webinar, please feel free to type your question in. We will dedicate 10 to 15 minutes at the end of this webinar to just go through all those questions and we will answer them. So please feel free to type them in. Thank you very much. Andres, please take it away.
Thank you for the introduction, Vadim. I want to give you an overview of deep learning and some of its usages. I'll present how you can efficiently use Intel's hardware to train and test deep networks. I'll share details on training on a single machine and across many machines. Finally, I'll show you how you can get started with Intel Optimized Caffe. Deep learning is a branch of machine learning. You take data and pass it through a series of nonlinear transformations, and the objective is to minimize some cost function. There are three main types of deep learning algorithms. Supervised learning, where you have data and labels, and you learn a model or function that maps the data to the labels. And supervised learning, where you have no labels, and is commonly used for applications such as clustering and dimensionality reduction. In reinforcement learning, learning occurs from rewards or penalties received given some input action. This is popular, for example, in robotics. Today, we will focus on supervised learning. In training, you pass the data, usually in small batches, through the network. You then compute a cost or loss based on the error between the network's output and the true labeled output. The partial derivatives, or the gradient of the cost with respect to the network parameters, is computed via backpropagation. The gradient of the loss with respect to the weights is used to update the weights. This cycle is repeated several times until the model is trained. The trained model can then be used for inference. The data is passed through the network and the output is computed. Deep learning has exploded in recent years due to the availability of larger data sets which are necessary to train deep networks, better hardware which reduces the time to train, and improved algorithms. There are various deep learning usages. For example, you can train a network for the task of image classification. The input is an image, and the output is a label such as person or bike. In this example, the input is an image and the output is a bounding box around every object of interest and a label for every object. You can actually train a network to return a label for every pixel, and this is useful for the task of semantic segmentation. In this example, the input is an image and a query about some object in the image. The output is a bounding box around the queried object. The green box is the network's output, and the yellow is the true or expected output. The input here is an image and a question about the image. For example, on the top left, what is the main color on the bus? The output is the answer, and in this case, blue. And where in the image the network found the answer? In this example, the input is an image and the output is a motor torque. Deep networks are popular in automatic speech recognition. In this example, the same network topology, with the exception of the last layer, is used to do speech recognition for both English and Mandarin Chinese. Deep networks are used in natural language processing. In this example, the input is a short story and a question about something in the story that may not be explicitly told but must be deducted, such as, where was Mary before the bedroom? The output is the answer to that question: cinema. This is very useful for companies to query a set of documents. Finally, most of us use deep learning in our everyday lives when we're assisted by tools such as Now, Cortana, Siri, Echo, and/or M. And there are many other applications for deep learning. Here you can see Intel solution stack from the hardware to the optimized libraries to the frameworks and to the deep learning tools used in order to meet the demands of various types of users across different market segments. So, do you need GPUs to do deep learning? The answer is a resounding no. But I will tell you later how the myth that GPUs are required for deep learning got started. You can do training and inference competitively on a general purpose CPU. Let's go through each part of the solution stack. Let's start with the hardware. Intel Xeon Phi with Omnipath Fabric provides an excellent platform to scale training across various powerful nodes and thus reduces the overall time to train. Xeon Phi provides up to 6 single precision teraflops, 72 cores, 512-bit SIMD vectors, and Omnipath provides dual port 50 gigabits per second for fast inter-node communication. Next year, Intel will release Knight's Mill, the next generation of Intel Xeon Phi. It will have more single precision teraflops and further reduce the total time to train. Now let's discuss the low-level libraries that are used for deep learning. There is a variety of deep networks, and they may seem very different. However, most of them are built from a limited set of building blocks. You can think of these building blocks as Lego pieces that can be assembled to create different types of networks. Some of these blocks are general matrix multiplies, or GEMs, convolutions, rectified linear units, hyperbolic tangents, etc. These building blocks, or low-level deep learning functions, have been optimized for Intel architecture inside the Intel Math Kernel Library, or MKL. Now, MKL is a library that contains many functions, and only some of them are used for deep learning. In order to have a more targeted library, we are releasing in the fourth quarter of this year Intel MKL DNN. A technical preview was released earlier this month with some functionalities. The library will be open source with the exception of the gem functions and will be released under an Apache 2 license. This will allow deep learning scientists to distribute the library and contribute new or improved functions. Optimizing low-level kernels is essential for performance. The best CPU, FPGA, or GPU gives poor deep learning performance if the deep learning functions have not been optimized for such hardware. Intel has optimized all the popular deep learning functions. However, prior to Intel optimizing these functions, NVIDIA was comparing the deep learning performance on GPUs using their optimized deep learning functions against Intel's CPUs with non-optimized deep learning functions. Obviously, the performance gap was large, and this created the myth that GPUs are much better for deep learning. The story is different now that MKL is optimized for deep learning. Now, for some workloads, Intel has a performance advantage, and for those workloads where Intel does not, the performance gap is small and is rapidly closing. Specifically, Intel MKL is optimized for AVX2 and AVX512 instructions, which are found in Intel Xeon and Intel Xeon Phi. This supports all common deep learning layers. We're continually improving the library. For example, we will soon be adding Winograd convolution, which is an efficient technique to do the convolution operation with a lower computational complexity, and is especially useful for small convolutional kernels, which are common in deep networks. Let me give you an example of the optimizations for one operation: direct convolution. For many deep networks, convolutional layers contribute to the majority of the compute task. In this slide, we see a simple but naive implementation of the convolution operation. And for those with a signal processing background, this operation should actually be called a cross-correlation operation, but we'll stick with the deep learning terminology. The operation is essentially 7 for loops over the batch size, the depth of the input array, also known as the feature map, the number of convolutional kernels, the height and width of the output array, and the height and width of the convolutional kernels. This implementation does not take maximal advantage of the CPU's low-level memory, registers, or instructions. The performance of this naive implementation on a CPU or some other hardware is very poor. On the other hand, this other implementation results in significant performance improvement on a CPU. The convolution operation is restructured to better utilize the cache hierarchy. The loop over output and input feature maps are blocked for on-die caches and allow for inner loop vectorization over output feature maps and independent fused multiply-add computations. The data is laid out so that in the innermost loop, accesses are continuous, ensuring better utilization of cache lines and therefore bandwidth, while also improving prefetcher performance. Register blocking is also used to improve reuse of data in register files, decrease on-core cache traffic, and hide the latency of the FMA operations. If some of the details in this slide don't make sense, check out the link at the bottom for the full paper. My main point is that we have done a number of operations that significantly improve the performance of the convolution operation and other deep learning functions for Intel architecture. The main building block or function of fully connected layers and of the various types of recurrent neural networks is the GEM operation. In deep learning, GEM operations are often performed on tall and skinny matrices. Over the past year, Intel has optimized for various matrix sizes for competitive performance. On top of MKL are the various frameworks used for deep learning. Intel is actively working to integrate MKL into the various frameworks in order to enable those framework users to run their deep learning training and inference workloads efficiently on Intel architecture. For example, Intel optimized Caffe is integrated with MKL. In addition, Intel has added multi-node distributed training capabilities to Caffe in order to distribute the training workload and reduce the total time to train. Later in the lecture, I will talk about distributed training. Intel recently announced the release of the Intel Deep Learning SDK. These tools accelerate the design, training, and deployment of deep learning models. The Deep Learning SDK allows the user to visualize the training progress, that is, visualize the loss, the accuracy on the validation set, the learning rate, etc. This information can help the user make decisions on how to change the model parameters to improve the overall performance. Once the model is trained, the Intel Deep Learning SDK can be used to quantize and compress the model, which is necessary when the model needs to fit in some particular hardware. In addition, the Intel Deep Learning SDK provides an inference engine. You can think of this as a lean and efficient framework that only does inference. Therefore, the trained model can be used for inference with the regular frameworks or with the inference engine provided in the Intel Deep Learning SDK. So this completes the overview of Intel's Deep Learning solution stack that can be used across a variety of market sectors. Next, let's focus on some of the technical details of training. Training deep networks boils down to minimizing an objective function. The goal of this part of the lecture is for you to understand the hyperparameter choices when training various models in order to minimize the objective function. Let's start with gradient descent. On the top right, you see the objective function computed as some value W0. W represents the parameters or weights of the network. In this slide, W has one dimension, but in practice it can have millions or billions of dimensions. In supervised learning, the cost is a penalty of how far the network's output is from the true expected output. The user can choose the cost function, such as the square difference penalty or the more commonly used square entropy penalty. When training a network with no prior knowledge of the search space, the first guess, W0, is usually chosen sampling some Gaussian or uniform distribution. Computing the derivative at W0 is used to determine the direction we move. If the derivative is positive, then you move to the left, and vice versa. In other words, you move in the direction opposite to the gradient. So the next position, W1, is the current position, W0, minus the gradient. Well, almost. We will add the learning rate alpha that scales the gradient. When training deep networks, this is one of the most important hyperparameters to choose. A poorly chosen learning rate will result in poor performance. If the learning rate is too small, it will take too many steps to reach the minimum. And notice that as you approach the minimum, the gradient gets closer to zero, and therefore the steps get even smaller. If the learning rate is too large and W1 is too far to the left, the objective function at W1 is now worse than at W0. That is, you are diverging and moving farther from the minimum. Here we have a good enough learning rate. We can continue taking multiple steps until we get closer to the minimum. One of the challenges with gradient descent are saddle points. You can get stuck in a saddle point and the training stops at a suboptimal value. In a dimensional space with millions of parameters, saddle points are a common challenge. Before we discuss a solution to saddle point, Here is a graphic of gradient descent in 2 dimensions. The red X is the initial guess, and the dotted green line is the path towards the minimum. Again, note that the steps get smaller as we move towards the minimum. In addition to the challenges with saddle points, gradient descent requires summing over all the costs for all the end training samples as shown on the top left. That is, you need to compute the cost for all the training samples before you can even take one step. In deep learning workloads, N can be millions or even billions, making gradient descent very inefficient. Stochastic gradient descent, or SGD, solves both of these issues. Note that the term stochastic gradient descent was originally reserved as a special case of mini-batch gradient descent with a batch size of 1, but now, including in this lecture, the term stochastic gradient descent and mini-batch gradient descent are used interchangeably. My apologies to a purist. In stochastic gradient descent, we compute a gradient, which I call the batch gradient, with respect to the loss of a small batch of training samples and not the entire dataset. The direction of the batch gradient, shown in red, will be different than the global gradient. Stochastic gradient descent solves the saddle point problem because while the global gradient at a saddle point is 0, the batch gradient, at least for some batches, will usually not be, and the model can move away from the saddle point. In addition, stochastic gradient descent allows us to make faster progress because we don't have to compute the error for the entire dataset. Over the next few slides, we will take many steps in the direction of the gradients computed from each mini-batch. Note that with stochastic gradient descent, the parameters initially make progress towards the minimum, but do not converge and bounce around the minimum. We can solve this by reducing the learning rate after every set number of iterations, where one iteration means doing stochastic gradient descent over one batch of training samples. This reduces the step sizes and improves convergence by getting closer to the minimum. Stochastic gradient descent with momentum further improves the training efficiency and accuracy. In stochastic gradient descent, while each individual gradient may not be in the direction towards the minimum, on average, the overall direction will be towards the minimum. We can take advantage of this by accumulating the overall direction of the gradients and taking steps in the direction of the accumulated gradients, known as the velocity. In the bottom right, the velocity is updated as a weighted sum between the previous value of the velocity and the current gradient. The momentum parameter mu is another hyperparameter to potentially adjust, but is normally set around 0.9. A graphical example can help. The red arrow is the gradient and the green arrow is the velocity. The bottom of the arrow is the current position in the weights domain, and the head of the green arrow is the next position. Over the next slides, we observe that the gradient modifies the velocity, and the velocity determines the next position in the weights domain. Even when a particular gradient points in the direction opposite to the desired minimum, progress in the desired direction continues. Another question to consider is what should be the right batch size, that is, how many training samples to include in one batch. While the exact answer depends on a particular workload, there are some general guidelines. As the batch size increases, the batch gradient approximates the global gradient, and the training starts to suffer from the same challenges of gradient descent. That is, training is slow because it takes more time to take one step, and because the training process can get stuck or greatly slowed down by saddle points. On the other hand, for very small batch sizes, the training time can increase because the processor may not be compute bound, and more computation is spent doing the various updates. So in practice, there is a sweet spot of well-performing batch sizes. For example, for GoogleNet, a popular topology used for image classification, the sweet spot is between 32 and 1024 images. We will return to this point later in the lecture when we talk about the challenges of distributing the training among the multiple nodes. One of the challenges in training deep networks is overfitting. Recall that in deep learning, we learn the parameters or weights of a series of transformations that map the input data to the labels. If the data is limited and the network has many weights, then we may be able to perfectly fit the training data to the labels. Isn't that great? Actually, it is not great. It is very likely that the network will do very poor on data outside the training set. That is, the network does not generalize. Let me share an analogy based on a regression problem. Suppose that you have 4 data points. The x-axis is the input and the y-axis is the output. You want to train a model that performs well for data outside the training set. If you choose a complex model, such as a polynomial of high degree, you can find a function that perfectly fits through all your data points. Your training error will be 0. If you choose a simple model, such as a linear function, your function will have non-zero loss. Then, for inference on a given input, each model will predict an output, denoted in red. When compared to the true output, denoted in green, you can observe that the performance of the complex model is much worse than the performance of the simple model. That is, the complex model was overfitting the training data. Using a complex model with only 4 data points for training is analogous to using a very deep network with few input samples. There are some strategies to avoid overfitting. You can increase your data set by collecting more data, and also by manipulating your existing data to augment your data set. For example, with images, you can crop various areas of one training image. For speech recognition, you can add various background noises. Other techniques are early stopping. As the network trains, you need to observe the accuracy of the network on a validation set, a data set that is non-overlapping with the training set. When the accuracy, on average, starts to get worse, then stop training. You can penalize large weights. Large weights can be a sign of overfitting. In Caffe, there is a weight decay parameter to adjust this penalty. Dropout. This is a technique for fully connected layers where a different subset of the weights are ignored in each iteration in training. The reason is to prevent co-adaptation, meaning weights working together to memorize a precise mapping from inputs to outputs. Training with single precision floating points instead of double precision adds quantization error, which helps to better generalize. Note that training with half precision is a research topic that is starting to show success for some networks, using some tricks not discussed in this lecture. Now you know what the training hyperparameters mean. When you train a network, you need to specify these hyperparameters. For example, in this Caffe solver prototext file, the hyperparameters are as follows. Base LR is the initial learning rate, or the alpha in the equations. Recall that during stochastic gradient descent, after some iterations, the weights kept on bouncing around the minimum, but they were not moving closer to the minimum. To solve this, you can reduce the learning rate after a given number of iterations, in this case 320,000, by multiplying the current learning rate by gamma. Max iter is the total number of iterations to train the network, in this case 10 million. In some frameworks, instead of setting a maximum number of iterations, we set a maximum number of epochs. One epoch means cycling through all the training data. Therefore, 10 million iterations with batch size 32 and total number of training samples 1.28 million, which is the size of the dataset used in the ImageNet classification challenge, is 250 epochs. Again, Caffe does not require explicitly specifying the number of epochs, but other frameworks do. Momentum is the mu variable. Usually 0.9 is a good value to use. Weight decay is not shown in the equations. It is a penalty for large weights to reduce the risk of overfitting. There are other hyperparameters in the solver prototext file. When you train a network, you should use two non-overlapping datasets, known as the training dataset and the validation dataset. The training dataset is used to train the model, and the validation dataset is used to test the model during the training process. This helps to verify if the model is overfitting the training dataset or if it is generalizing and performing well on the validation dataset. Test interval is the interval of training iterations that the model will be tested with the validation dataset. Test iter is the number of iterations to test the validation dataset. Snapshot is how often should the model be saved. This is useful in case the computer crashes or to analyze the models at various training stages. Snapshot prefix is the location and prefix name to save the snapshot from the Caffe root directory. Solver mode can be set to CPU or GPU. At the end of the lecture, there is a link with a tutorial I wrote that explains in more detail the various hyperparameters that can be chosen. But how to choose hyperparameters? The answer is experience. Look through examples and practice modifying them. Let's talk about how to train using multiple nodes or machines. There are two general methods. The first is using model parallelism, where the model is broken into the n nodes, and the same data is in all the nodes. The second is data parallelism, where the data is broken into the n nodes, and the same model is in all the nodes. Intel Optimized Caffe has data parallelism capabilities for distributed multi-node training. This is good for deep networks with few weights, such as GoogleNet. Using a hybrid approach with both model and data parallelism is also possible, and incorporating that into Caffe is work in progress. In data parallelism, a batch size is broken into n nodes or workers. For example, if the batch size is 512 and there are 32 nodes, such as in this example, each node has a batch size of 16. 16 times 32 is 512. Each worker does a forward and backward propagation and computes the gradients, but does not yet update its model. The gradients across all the nodes are first aggregated, and then the models are updated with the aggregated gradients. The resulting model is the same as if one node had done all the work, with the complete batch size. This type of model updates are known as synchronous updates. On the other hand, the topic of asynchronous updates for deep learning is a research topic that is not covered in this lecture. Now, there are various ways to efficiently aggregate the gradients and communicate the updated weights, such as tree, ring, or butterfly or reduce, and broadcast algorithms. And for linear scaling, the communication of the gradients and updated weights needs to be hidden in the computation. That is, you need to have the communication in the computation. Using these techniques, Intel has achieved near linear scaling to 32 nodes on GoogleNet, significantly reducing the time to train from days to hours. But why not scale to thousands of nodes? Well, there are some challenges. Remember that there is a sweet spot for batch sizes. To scale, you want the largest batch size that performs well. Even if the dataset is millions of samples, the largest batch size is usually in the hundreds or low thousands. So assume the largest batch size that gives good performance is 1024. That means that you cannot scale to more than 1024 nodes. If you have 1024 nodes and a total batch size of 1024, then each node batch size is 1. However, to scale well, you need to have the communication in the computation. Given that the computation is very small and the communication is large, then you won't scale well. A better setup may be using 64 nodes and a node batch size of 16. If you have a fast fabric such as Omnipath, then most of the communication can be hidden and you can scale well. As you find the sweet spot and adjust the batch size, a good rule of thumb is that the batch size is correlated with learning rate. Not necessarily linearly correlated, but start with linear correlation and then adjust accordingly. In this lecture, I have covered the basics of the training process, but I have not explained how to design a model or the differences between the various types of deep networks or the differences between the various frameworks. Those are also important topics that we'll cover in other lectures, so stay tuned. But let me share a secret about deep network designers. We rarely design a network from scratch. Rather, we find a network that has worked for a related application and modify that network to fit our own application. Now, to get you started using Caffe right away, I put together a tutorial with detailed instructions. After installing Caffe, following instructions, I recommend jumping to the example section to get some hands-on experience before reading the details of each section. The training section explains how a model is defined and trained. A deep network is built out of building blocks, and each one has a number of parameters. This section shows examples of model definitions and the parameters used for each building block. The fine-tuning section explains how you can use a model that was trained on a large data set and use it as the initial weight to train a model with a smaller data set. There are a bunch of pre-trained models available at the Model Zoo that you can find at the link in the fine-tuning section. You should be able to design deep networks in Caffe after reading through the tutorial. Some resources are the tutorial I just introduced and the Deep Learning SDK that was introduced earlier in this lecture. We're optimizing many frameworks for Intel architecture and have made available Caffe and Theano with others coming soon. Thank you for your time and stay tuned for future deep learning webinars. I am happy to take your questions.
All right. Thank you, Andres. I really enjoyed this presentation. Thank you very much. I think it was a perfect introduction into deep learning and what Intel is doing actually in this field. So how about we switch to questions now? I suggest I will just read some of them because we have actually quite a lot of questions. But still, guys, you can use chat window and ask questions. We have almost 20 minutes to go through them, so we will try to answer as much of them as possible. So the first question we have is more generic. What is the difference between machine learning and deep learning? Andres?
Yes, machine learning is a much broader field. Deep learning just focuses on a subset of machine learning where the algorithm is essentially a set of nonlinear transformations. And the deeper the network is, the more nonlinear transformations you are performing.
Mm-hmm. All right. Good one. Next question. What learning type would natural language processing be a class as?
So I think this question is asking whether this is a supervised learning or unsupervised learning or reinforcement learning.
Correct.
So natural language processing involves a different number of applications. It can mean from machine translation to sometimes people categorize automatic speech recognition within natural language processing. And it can also mean understanding content from within a text. Usually, it's in these examples, these belong to supervised learning. So, for example, if you're doing machine translation, where the input is English sentences and the output are French sentences, then you train your network with a lot of examples from English to French. And then when you're testing or deploying the network, then you would just give English as the input, and then the network would have learned to map those English sentences to French sentences. So when the model is deployed, then you just give English sentences and the network will automatically produce French sentences. Now the details of exactly how to build this type of network were of course not covered in this lecture. I would like to cover some of these details in future lectures.
Oh, so you're basically saying that there will be deep learning 102 webinar. That's great, actually. All right. So next we have a couple of questions about hardware. So the first question, where is the performance bottleneck in terms of hardware and what can be improved? Is CPU cache utilized?
The bottlenecks, it depends on the type of application. So sometimes for some applications usually you want to be compute bound. And so that means you want to utilize the low-level cache memories. And in the naive implementations of some of these deep learning functions, we were not compute bound a year ago. But over the past year, we've done a lot of work to rewrite these naive implementations so that now we can be compute bound we can reuse the low-level cache memory and therefore improve the performance of these deep learning functions.
Right, and convolution now implemented as GEM operation, general matrix multiplication, which is a compute bound and optimized for cache reusage if you're using it from MKL library. So MKL implementation is heavily optimized for cache reusage, and it is definitely compute bound. But everything depends on your matrix size, right? So there might be some issues there. All right, so let's switch to the next question. How many cores are used in deep learning? Is there a true advantage using multi-core CPU against single socket CPU with a higher frequency?
So we try to, MKL uses all the cores that are available, and you can limit the number when you invoke. So when you invoke, for example, Caffe, you can limit the number of cores that you allow MKL to use. But if you do not limit the number of cores, then MKL will use all the cores available in your system.
I see. So next, the question about our plans. Is there a plan to create Intel-optimized libraries with algorithms like BFGS?
We're always improving the functions in MKL as academia discovers or brings to our attention, not just academia, but also industry researchers develop new functionalities that are showing good performance, then we will be including those in MKL, or we'll be improving the current functions that we have in MKL. For example, Winograd convolution, which is an efficient way to do convolution, will be added to MKL in the near future. But one of the benefits of the open source library we'll be releasing next quarter, MKL-DNN, is to give the community the opportunity to also contribute their own implementations. So, the world's much more able to rapidly add new functionalities. So MKL-DNN provides this capability for researchers to be able to put new functionalities into MKL-DNN.
Right, because MKL-DNN will be open sourced, right? So everybody can contribute to it and implement new deep learning primitives. That's going to be great. All right. So next, we have a couple of questions about deep learning techniques, actually. Instead of limiting momentum, can we use the rate to change of gradient to filter step slopes?
So one of the benefits of using momentum is that you gain velocity in the direction that you want to move towards. And if in the high dimensional space, if for example, there is a point where you are in an area of a local minimum, a shallow local minimum that you want to get out of, with momentum you can more easily get out of this shallow local minimum and continue your descent towards a better minimum. So momentum, it's pretty important in these deep learning applications to find a good local minimum.
Right. Okay, and then there is also a question about programming languages. So does it support Python language? I assume the author of the question was asking about Caffe deep learning framework.
I missed the last part of the question, but let me answer what I understood, and you can correct me if I left anything out. Caffe, both Intel optimized Caffe and MainCaffe, it's programmed in C and C++ with Python and MATLAB bindings. So you can define your functions, your network, and also your functions in Python or in MATLAB. Now, other frameworks such as Theano or TensorFlow, they are built on, or Neon, they're built on top of Python. So all the functions will be based on Python for those frameworks.
I see. All right. The next question is back again to deep learning techniques. So does gradient descent consider all the training examples in each iteration?
Gradient descent does consider all the training samples, which is a problem for two reasons. One is it takes a long time for gradient descent to just take one step. I mean, one iteration, it requires you to process the entire data set. And if the entire data set is millions of examples or billions, then it becomes unfeasible to really train these networks. And the second problem, as it was discussed in the lecture, is that you can easily get stuck in a saddle point doing regular gradient descent. And there are many saddle points when you think about a 60 million dimensional space, which is the dimensional space of a popular network like AlexNet. So gradient descent is not the right approach to use in finding a good minimum in deep learning.
What about stochastic gradient descent?
Stochastic gradient descent, which is a variant gradient descent, is a solution to the issues that gradient descent has.
Right, and it's not using all the training samples, right? It's using only a subset of them.
It processes all the training samples, but it does it in batch sizes, in small subsamples, so that as you progress down towards a minimum, you take multiple small steps instead of one step having processed all the images, all the samples.
Okay, and we actually have two questions related to precision. So the first one, you didn't cover this, but what is the difference between fixed precision, single precision, and integer? And the second question, I think it kind of relates, changing CPU vector processing unit from double precision, single precision to half precision, would this benefit the training phase or the categorization phase? I think we refer to inference, and why?
So, they're very good questions. When you're training deep networks, the main goal is not to have the best performance on the training data, but you want to have the best performance on a general data set that is not part of your training data set. So one of the ways, in other words, you don't want to overfit the training data, as I covered in the lecture. One of the ways you can avoid overfitting to the training data set is by adding noise to your model. One of the ways to add noise is by reducing the precision from double to single precision. And what the deep learning community has observed is that single precision is sufficient for training deep networks. Now, the question is, well, can you go to half precision? Going to half precision is currently a research topic. There are some methods that are used. If somebody's interested, they can do a search for stochastic rounding, which is a technique used to improve the accuracy when you are training using half precision. But half precision training has not been widely adopted in the deep learning community. But we are moving towards that goal, because if you can train with half precision, then you can potentially train twice as fast. Now the question is for inference, or as some people call it, testing or deployment, we find that half precision is sufficient to get good performance, to get equivalent performance to single precision in inference. Now, another question I think was asked, what about a fixed integer or
Yes.
or a floating point? As you move down from half precision to a quarter of precision, which is a research area for inference, again, not for training. For training, the current research topic is from single precision to half precision. For inference, the research area is from half precision to a quarter of precision. You don't want to use floating points when you have only 8 bits, because you don't want some of your bits to be used for the exponent. That would greatly decrease the range of numbers that can be represented. When you are around 16-bit or at 16-bit, the range of numbers that can be represented with fixed integers or with floating points, it's roughly equivalent. The number of numbers that can be represented is roughly equivalent with fixed integer, with a 16-bit fixed integer to have floating point precision.
All right. We actually have quite a lot of questions about if the recording of this webinar will be available. And yes, it will be available. So if you just use the link you've used right now, you can simply rewatch this whole webinar or portions of it. So it will be recorded and it will stay online. So the next question, and probably we're going to wrap up soon, how to decide the batch size and learning rate? Is it totally based on experiments, or there is any theoretical formula?
So this is a little bit of the what people call the black magic of deep learning. There are some relations between batch size and learning rate, in that as you increase the batch size, then you can essentially take larger steps. And so there tends to be a somewhat linear correlation between batch size and learning rate. And there are some mathematical theories that show the correlation. But in practice, you want to tweak those parameters. So when you train networks, what you end up doing is first you designed the network, and we didn't cover in this lecture how to design a network, but hopefully the tutorial that I pointed out in the lecture can help you design a network. But once you design a network, you need to tweak these hyperparameters, such as the learning rate. And the way you can do it is start by using a learning rate of let's say 10, 3, 1, 0.3, 0.1, 0.003, 0.001. So you usually do a sampling across various learning rates. And similar, you can also sample across various batch sizes. So it does take extra work when you're first looking for a good set of hyperparameters, but you don't have to necessarily train the network for thousands of iterations. You can, for a set of hyperparameters, you can observe how the training is going after a few hundred iterations, and then decide whether or not to continue training because the training is improving your accuracy, or whether to stop and choose a different set of hyperparameters.
All right. Thank you, Andres. So we have actually one question about MKL again. Do you have any case studies using MKL? Can you name any ML machine learning software using MKL? I can probably answer this question quickly. There was a Intel Python distribution released just recently with Python linked to MKL and NumPy libraries, all the BLAS routines, basically algebra routines. Instead of using their original Python implementation, they switched to this heavily optimized, multi-threaded, vectorized version of, let's say, general matrix multiplication. And there are a few white papers published on Intel on our IDZ, Intel Developer Zone, which actually demonstrates the benefits of using those heavily optimized libraries. So yes, there are examples, and you can find them online. There are several white papers discussing this. So we're probably I'm gonna ask you two more questions, and we should probably wrap up because it's already past 10. So I actually like this one. What are some more good sources to find already trained models that one can use as example and modify to fit a new need?
This is a great place to get started when you are new to deep learning, which is find a model already that exists and modify it to your application. A good place to get started is to search for the Caffe Model Zoo. So if you do a search for Model Zoo, you'll find a collection of various models. Some of them you can use without any restrictions in commercial applications. And a number of those models are models that both researchers or practitioners have shared with the overall community. So somebody has developed a model that works for specific applications, such as this model works great for both detecting and recognizing objects in images. And then they post that model on the Model Zoo, and then you can use that model depending on the restrictions that are associated with that model.
Great. And I guess that will be my last question. Is there any resources people can go to find more information about machine learning, deep learning, and what is Intel doing in this field?
Yes. Then why don't you actually share the address of the Intel Developer Zone with respect to deep learning?
Sure, I can do that. So we actually have the whole zone dedicated to machine learning. It is software.intel.com/machine learning. And actually we have a special page down there related to deep learning. So you can find all the information, our vision, where it's all supposed to go, and just stick tuned. There will be a lot of information published there pretty soon. So at this point, we actually have dozens more questions, but unfortunately we ran out of time. So thank you guys for participation. We'll try to stay in touch. There will be second webinar, maybe even third and fourth, we'll see. Andres, thank you very much for your insights, for all the information you shared. I really enjoyed this webinar. So thank you guys, and stay tuned.